Hi, welcome to this lecture on computing components and operation. My name is Professor Judah. So in this lecture, we will explore the technology that makes computing possible. So we will begin by exploring two computer architectures called the Harvard architecture and the von Neumann architecture. We then focus on the central processing unit and the graphics processing unit. So this is the CPU for central processing unit and the GPU for the graphics processing unit, which are really the driving forces behind the computational and graphical capabilities of any system. Thereafter, we'll examine memory and storage solutions for data storage. We will then discuss the motherboard, which basically connects all of the components within the computing system. At the end of this lecture, we will briefly discuss some categories of input and output devices. So let's begin with the von Neumann architecture. The von Neumann architecture, despite being introduced way back in 1945, is mainly seen as the blueprint for designing modern computers. In this architecture, we have four main components. On the screen, you can see in green the arithmetic or logic unit. That's called the ALU. We also have the control unit, the memory unit, and the input and output mechanisms. So those are where your devices are connected to for input and output. So we'll discuss this at the end of the lecture. The main principle behind the von Neumann architecture is that a computer can store instructions and data in a single read-write memory. So you can see the instructions as well as the data for which the instructions concern is stored within this bottom blue block called memory. So in other words, since instructions and data are both written in the same format, right, which are strings of binary numbers, then they can be stored in the same place because memory can facilitate binary numbers which can represent either instructions or data. So memory is really organized into addressable units, and each of these units is capable of holding a small amount of data or instructions. So the small amount of data in this case can be a 0 and 1, and together these blocks of memory give us our instructions. At the center of the architecture, right in the middle, where you see this inner block here, is the central processing unit. So we call this the CPU. And the control unit, which is above it, the arithmetic logic unit, and these smaller sets of registers, the AC, PC, CIR, MDR, and MAR, all together give you the CPU. So we'll talk about those registers in the next section. The control unit orchestrates the operations of the computer. It acts as you can imagine it as the conductor. It fetches instructions from memory, it decodes them, and then it sequentially executes these instructions. The control unit also directs the flow of data between the arithmetic or logic unit, which is the green one, memory, and the input and output devices. So it really is a conductor. And all of these different components, you can think of them as members of the orchestra. So what is the responsibility of the ALU? The ALU is responsible for carrying out all of the arithmetic and logical operations. So arithmetic operations are things like adding or subtracting or multiplying, basic arithmetic. And you've already seen examples of how to build these using circuits in the previous videos on full subtractors and half subtractors. The logical operations that it also performs are things like ORs, ANDs, bitwise shift operations, exclusive ORs. It can also perform operations such as like those. So these operations are very much the core purpose of the ALU is addition, subtraction, and, or, not, and so on. So that's why it's called arithmetic or logic unit. Okay, so what else do we need to talk about? Those registers. So within the CPU, right, so that's this section here within it, we have these registers. These registers are small, fast storage locations. So the main registers that we will talk about is the accumulator, which is the ACC. In this context, it's just AC, but often when we refer to it, we have the abbreviation ACC for accumulator. And what is the purpose of the accumulator? It just temporarily stores data from operations. We also have the program counter, which keeps track of the next instruction to execute. We have the memory address register, which is the MAR, which holds the address of the memory locations being accessed. Okay, then we have the memory data register, which is this MDR, which contains the data being transferred to and from memory. We finally have the current instruction register, which is the CIR, which holds the current instruction being executed. So we're going to see how all of these things fit together on the next few slides, and to be able to execute instructions. Finally, the input and output components of the von Neumann architecture are just the channels through which the computer interacts with the external environment and the user. So they allow for to retrieve data from input devices, such as if you're typing on a keyboard, or if you have some sensors that are picking up information from an environment. And this is sent to processed inside. That's why it's a computing course. It's processed within the CPU, and then whatever is the result of that is output into maybe displays and printers. So that's basically what that does. So to contrast this with a different architecture, on the screen you have something called now the Harvard architecture. So the Harvard architecture, the big difference here is that it physically separates the storage and the handling of CPU instructions and the data, which sometimes leads to more efficient processes. It's a bit of a mouthful, but if you look at the only difference here between these two is here you have the clear distinction of the input and output, but we merged them here together, but it doesn't really matter because you can think of them as two separate lines that go in and out. But the big difference here is this memory, the blue block, which has memory. That now is because remember I said before that instructions and data both have the same format, right? Which is binary. So in this architecture, the von Neumann architecture, we store it in the same place. However, in the Harvard architecture, we store the instructions in one component of memory, and we store the data that involve those instructions in a different component in memory. Okay, so I mean, having the split assists with some performance gains, but despite these performance gains, the Harvard architecture introduces increased complexity because now you've got two different places where you're storing things. And this translates to devices with larger physical sizes. So you might have a bigger device. And also a bigger device means that it probably costs more to manufacture that. So their production cost increases too. So it might not be worth it. So, well, additionally, we also have the separation of the data and the instructions, which also, I mean, in a way, limit our flexibility in programming. Because now, if you remember from the lecture we did on software, we could store the data, the variables after the program, and then we would just simply refer to the different components in memory to be able to get that data for any instruction. But now having it in a different separate component in the architecture, we would need to go to a different place to go and actually retrieve our variables, the information that our variables contain. Okay, so the Harvard architecture is really used in real-time applications and high-performance computing environments. So what's common between this von Neumann architecture and the Harvard architecture? So we see here, well, the thing that's common between them, if we can see the input and output moves around, the memory moves around, but the thing that's really common here is the CPU, right? So let's discuss that first because that's really a main component of these architectures. So the CPU, so what is the main operation of a CPU? Okay, this is the part of the class when I'd ask you that question. And one of the smart students will raise their hand and say, the main operation of the CPU is to simply execute instructions. So let's talk about that a bit more. So the CPU is made up of several components. So I've highlighted these different components for you on the screen. So yeah, so what are these different components? Well, we see that there's this thing at the top called cores. So the core 1, core 2, core 3. So these cores make up about 40% of the CPU. It's quite a large component. It's almost half. And these are the actual units of processing. Each of these cores comprise of a arithmetic logic unit, and that arithmetic logic unit performs basic operations. It also contains a control unit, and that control unit, like I told you, was the director. It moves things, it acts as the coordinator for what's going on inside of the CPU. And the other thing there's registers, right? Registers are basically just temporary data storage devices. And you get a level 1 cache for rapid data access, so a very close storage within the core where you can store information. So you do have other types of storage in a computing system, but the one that's inside of the core is called the registers. It's called a cache. And then finally, you have the FPU, and that's called the floating point unit. And what that does is numerical calculations. So these different components of a core is just this control unit, the ALU, the registers, the L1 cache, and the floating point unit. So then we have cache memory, which is this part here at the bottom, this L3. That accounts for about 30% of the CPU. And it is divided into level 3 cache and level 2 cache. And the purpose of this cache is really to optimize data retrieval. So it allows us to store information that we're working on inside of the CPU itself, so that we don't have to keep going out of the CPU into memory and store information. We then have another component here called the memory controller, and that's about 5% of the CPU. The purpose of the memory controller is just to oversee data flow between the CPU and memory. So as the name suggests, it controls this interaction between the CPU and memory outside of the computing system. The prefetch unit and the bus interface unit, these manage the data prediction and communication with other devices in the computing system. Finally, we have in the CPU a clock, and it looks like such a small little thing in the corner here, the clock. But this is a very important component. And the purpose of the clock is to synchronize all of the CPU operations. So we have maybe an instruction, let's say for example, 5 instructions per clock cycle that is executed. So it really is the heartbeat of the CPU. So the clock synchronizes the CPU operations, and the instruction decoder, which is the blue thing over there, which makes up about 10% of the CPU, this translates instructions into executable actions. So there are other computing components inside of the CPU, but I'm just going to call those other. So these are the most important components of the CPU. So I've written them down here, the important ones that I've spoken about. Here you have the control unit, the arithmetic logic unit, registers, cache, clock, bus interface unit, and the floating point unit. So like I said, there's lots of different components of the CPU. But if you can just know what these are, then at least you can you know enough to have a conversation about what the CPU actually does. So I'm just giving you a few seconds to look at this, and then I'll move to the next slide. Or you can just pause, I suppose. Okay, so that brings us to the main it brings us to the main function of the CPU, and that is just to execute instructions. So how does this execution of instructions actually happen? So it happens via a process called the fetch execute cycle. And the fetch execute cycle involves retrieving instructions, decoding them, executing them, and then storing the results. So here in front of you, I've drawn a picture that tries to illustrate the high and low level processes involved in the fetch execute cycle for a 24-bit machine. So this is a 24-bit machine. So like I told you before, you can have 64-bit machines, which is what our computers use today. That means that the instruction format is in 64 bits. You can also have 32-bit machines. For this example, just to keep things very simple, and also which makes it relate very nicely to the software class, we have a 24-bit machine. So when I say software class, I mean the lecture we had in class on software. So here, the general cycle of the fetch execute cycle, and this kind of figure is very difficult to actually visualize. So I'm going to try to zoom in, and you can see here there's it's difficult to put onto one slide. As you can see, it's a very difficult, very complicated picture. But I'm going to try to zoom in. So I hope you can see it now. I also hope that this is recording in high quality. So there's these two cycles. There's the fetch cycle, and then there's the execute cycle. So the fetch cycle is this blue part over here. So all of this here, this part here is all the fetch cycle, and then the part here at the bottom is the execute cycle. So it's like how you would fetch an instruction and then execute this instruction. So the fetch cycle is the blue region, and the execute cycle is the green region. So the fetch cycle involves retrieving the instruction from memory and decoding it. So fetching it and deciphering it, decoding it, okay? And the execute cycle section at the bottom, that involves retrieving any associated data from memory. Okay, so that means that in the execute cycle, we have to go to memory and fetch whatever is necessary to get from memory. And then, so the execute cycle, it's retrieving any associated data required from memory, and we use that data to execute the instruction. So that means we finally have to execute it. So in other words, we get the instruction, we decode the instruction in the fetch cycle, and then in the execute cycle, we get any data related to that particular instruction from memory, and then put it together with the instruction, and then after that, execute it. So that will be the execute cycle. Okay, so during the fetch instruction phase, which is this part here, okay, so we're looking at the top part now. So now we're looking at the fetch instruction phase, which is how we actually retrieve the instruction from memory. Okay, so we're flowing from top to bottom. So during the fetch instruction phase of the fetch cycle, so that the blue region at the top, the computer retrieves the instruction from a place in memory called RAM, and the RAM stands for random access memory. So that RAM is the red block. There's a red block on this side. I'm going to move the mouse so it doesn't cover anything up. So that red block there looks very similar to how we address things in the software class. And it tells us that there is data and instructions stored somewhere in that red block. So now we need to know where to start and how to actually index these particular instructions. Okay. Right, so then let's go through this slowly so we don't get confused. So during the fetch instruction phase, the first of 4 phases, the first of 5 phases, the computer retrieves an instruction from RAM, from random access memory, the red region. So we will refer to the specific type of memory, this RAM, as just memory. So for the sake of this discussion, let's just say it's just called memory. We won't refer to it specifically as RAM. So we've got at the top there the program counter. So that's our PC. So that holds the memory address of the next instruction to be executed. And we need this in order to be able to find the next instruction to be executed. So this address is transferred to the memory address register in the diagram. The memory management unit, which is the MMU, uses this address to fetch the corresponding instruction from memory. Okay, the instruction is then retrieved using something called an address bus and a data bus. So the address part of the instruction, the address gives us where is the particular instruction. So the memory address register will tell us where to look. So if you can see there in the memory address register, there's a 1 which indicates a 3. So in our memory, which is the red region, we have address and we've got a 3 there, which means that the instruction that we are particularly interested in retrieving is at memory address 3. And we know that it's a 24-bit instruction, so we just have to go and get that entire block of 0s and 1s. So we retrieve it with the data bus. So the address bus tells us where to look, and the data bus brings that data to the memory management unit. Okay, I hope it makes sense so far. So the memory management unit uses the address to fetch the corresponding instruction from memory. The instruction is retrieved using the address bus and the data bus, right, which connects the MMU to memory. Okay, that's just recapping what I just said. Okay, so far so good. So now we've got the instruction and it's sitting in our memory management unit. So what's the next thing that we need to do? So now we've got to actually put that instruction in a little register where we can retrieve it. So we put that in the memory data register. So while this is all going on, the program counter actually indicates the next instruction after that. So the instruction that we're working with right now is this is at address 3, okay, indicated by the memory address register. And while we are retrieving all of this information from memory and all of this stuff, the program counter iterated. Okay, can you see there? It adds by 3 because it moves in 3 blocks at a time. So that program counter is interacting with a 3. So the program counter iterates to indicate the next instruction to be executed. Right, this is done concurrently, like I said, by adding the word length of the processor to the program counter. Okay, so here there's the word length here is 3 bytes, which is why it's written there at the top plus 3, because it's 3 bytes, which gives you 24 bits. The fetched instruction is then stored into the memory data register, which is the MDR, this one over here at the bottom, and is subsequently moved into the current instruction register, the CIR. So now we are in the control unit. So once that happens, we are in the control unit. And in this control unit now, we will decode the instruction. So in the decoding phase of the fetch cycle, we're still in the fetch cycle, the CIR separates the instruction into 3 components. Okay, we have the operation code, we have the address mode specifier, we have the operand specifier. So that's these 3 components at the bottom over here. And now we actually have identified the components of the instruction. I've color coded it. So the operation is in red, operation code is in red. The orange is the address mode specifier, and then the operand specifier is in blue. Okay, so you see the color code, right? And now that we've segmented the instruction in the CIR, we can actually, we are in the process of decoding it to find out what does this instruction actually mean. So this decoding phase identifies the address mode specifier, which tells the CIR where to send the operand specifier. So the address mode specifier, if you recall, tells us something about whether we should whether we have the address that we of the thing we want from memory, or do we have the actual thing itself. So at this point, we are at the get data phase of the execute cycle. So that's where we are now. So do you see this? We are now in the execute cycle. So the operation code now with the address mode specifier tells us where to go. So we again in the memory management unit. So obviously this memory management unit and this memory management unit is the same unit. It's just that I've duplicated it here to show you how it relates to the different parts of the cycle. Okay, so we are now in the get data phase of the execute cycle. If the address mode specifier represents direct addressing, so that could be 001, right? I mean, I'm talking now about the orange, those 3 bits in the orange. So if it's 001, okay, we often denote this as a D, then the operand specifier actually specifies an address to memory where the operand can be located. The CIR would then need to send the operand specifier to the memory management unit, the MMU, to fetch the operand from memory using the address bus and the data bus, just like before. The data retrieved from memory is then sent to the ALU, so whatever is then retrieved. If the address mode specifier represents immediate mode addressing, which is 000, denoted by an I, then there is no need to retrieve anything from memory because the operand specifier specifies the operand and not an address to the operand. And the operand specifier can then just be sent immediately to the ALU. So the CIR, which is the register, the current instruction register, also sends the operation code, which is decoded in a table inside of the CPU called the instruction decoder. And you can think of the instruction decoder as that little table that I asked you to draw in class, where you add the operation code and the meaning. And there it just decodes the instruction for us. So if it's in this case it's a 0111, then the instruction decoder says, well, it's an add instruction. So can you see then add is then sent with the operand specifier, whether it comes from the memory management unit, with the operand from the memory management unit or the operand from the instruction itself, it goes into the arithmetic logic unit. Okay. Okay, so the good thing about a video is you can always rewind if you misunderstood something I've said. Okay, so let's try to think about where are we now. Okay, so we are now in the execute instruction phase of the execute cycle. And this is where the instruction is actually performed. If it's an arithmetic or logical operation, it's carried out by the ALU. So the ALU only needs an operator, which is either to add or subtract or to do a binary shift or whatever. And it needs two operands to execute the instruction. So for example, to perform the addition 2 plus 4, you would need the operator, which is the plus, the two operands, which are 2 and 4. So this means that the ALU has almost everything that it needs to be able to execute the instruction. It has the operand, which is specified by the instruction decoder, and it has the operator, which is decoded, which is represented by the instruction decoder, and it has one of the operands, which is supplied by either the MMU or by the CIR. So where is the other operand? Well, the other operand is already in the accumulator, which is directly connected to the ALU. So that's the green region here for this is the green region, the accumulator. So notice also here we had these 5 different phases, right? The fetch instruction was at the top here, then we decoded the instruction here, then we got the data, and then we executed the instruction. So that's where we are currently. Okay. So with all of this information, the ALU now is able to interact with the accumulator to be able to execute the instruction that needs to be executed. Okay, so the control unit here, the one that has a dotted line there, it has a set of registers inside of it. So we didn't speak about these registers while we were still in the fetch cycle, but these registers are really relevant to the execution cycle. And these registers are called status bits. So these little bits over here, the status bit sign, the status bit parity. I see status is spelled wrong. Status bit 0 and status bit carry. And there's more than 4 of them, but in this example we just have these 4. So the status bit sign is set to 1 if the result in the accumulator is negative, and it's set to 0 if it's positive. This is following the instruction that just occurred. The status parity bit is set to 1 if the number of bits in the result is even, and 0 if the number of bits is odd. And the reason why we have that is often for error checking, right? So remember the whole error correction and detection, we can even do that inside of the CPU. So that's what that bit is generally used for. Then we have the status bit 0, which is set to 1 if the result of the operation is a 0. So that means what's in the accumulator becomes a 0, which indicates a null result. And finally, we have the status bit carry, which is set to 1 if an arithmetic operation which is done in the accumulator results in a carry out of the most significant bit. So that tells us about, it helps us detect overflows. So you can imagine if there is a number in the accumulator and we add 1 to it and it results in a overflow, then we want to know about it because maybe that's not what we intended to do. So we allow the control unit to have some kind of indication if that actually happens. Yeah, so that's basically it from that side. So these status bits really assist the control unit in making decisions about the flow of the program execution and in executing subsequent operations. So once the execution is complete, the results of the computation are often written back. So that's now the last state, the red one at the top over here. So that's the write back. So we say it is often written back. Sometimes it is, sometimes it isn't, and it is generally to a designated register or memory location inside of memory. So specifically, the result of an operation is stored in the accumulator, which is then written back to memory via the memory management unit for storage. So I mean, because often you want to compute something and then store it. So the write back phase really allows the results of any instruction to be available for subsequent use. So that's the big idea behind it. So now that the write back is completed, the computer can prepare for the next instruction. So lucky for us, the program counter is not lucky for us. It was strategically done. The program counter already is updated with the address of the next instruction to be executed. Remember, it was done subsequently while the instruction was being passed around. The program counter incremented. And so it's already updated with the next instruction to be executed. And so the cycle starts again from the fetch instruction phase, going after that to the decode instruction phase, and so on and so on. Okay. And the cycle basically repeats on and on and on while the computer is always in operation. Instructions like this are being executed. So each instruction in a computing system must pass through all of the phases, all of them, of the fetch execute cycle to be fully processed. Okay, so it really has to pass through all of those 5 phases, and there's no exceptions. So, but however, only one instruction uses the fetch execute cycle at a time. Okay, so then that means that while one instruction is going through these different phases, the other phases remain idle, waiting for the instruction to complete so that the next instruction can then go inside and use the 5 phases. So for instance, during the execution phase, the fetch, the decode, the get data, and the write back stages are typically idle. So this implies that at any given moment, only a fraction of the CPU's resources are actually being engaged in processing. So well, to address this inefficiency, there's different ways of parallelism, which is ways of using the CPU to its better potential. And there is a particular type of parallelism which is called instruction level parallelism. And this technique is a type of what we call pipelining, which allows multiple instructions to be processed simultaneously within different stages of the fetch execute cycle. So the relative independence of each phase allows one instruction to be fetched while another instruction is being executed. This approach basically maximizes CPU utilization by making each phase of the cycle continuously work on a different instruction. And you can think that this is actually quite, if we could get this right, that means that we will be using all of the CPU's resources efficiently. We'll be able to be using all of the different states of the CPU. So just to go back one slide, we have the fetch instruction, the decode instruction. So if we have an instruction, it first goes to the fetch instruction, then the decode instruction, then the get data, then the execute instruction. But once that instruction is here, all of these are done. So why can't we start another instruction simultaneously? While this instruction is at the execute instruction or at the get data or even at the decode instruction, why can't another instruction be fetched? Okay, so you might be thinking, well, what's the problem with this? And you're right in thinking, well, it can't be that easy. There must be some kind of problem with it. So executing multiple instructions concurrently can lead to conflicts. So these conflicts are called hazards. And these hazards arise when instructions in close sequence interfere with each other. So maybe instruction 2 requires some information from instruction 1. Then we can't possibly start executing instruction 1 when instruction 1 hasn't yet finished. Because maybe there was something important for instruction 1 to do in order for instruction 2 to complete. So maybe instruction 1 was loading some information to the accumulator, and the other instruction has to then add something to the accumulator. And so we can't really run them because maybe you could have a situation where instruction 1 needed something from a particular address, or instruction 2 needed that wasn't yet updated. So I mean, it's yeah. So let's not speak so hypothetically. Let's actually look at a practical example. So here we have a practical example. So the whole problem with these hazards is that they cause unexpected issues, and so we need to be able to handle these hazards in order for correct program execution. So let's look at this example. Suppose we've got the following two instructions. So we've got the instruction R1, which is to add 2 to 3. Okay, so that's what we have there, and that adds the values in the registers R2 and R3 together and stores the result in R1. So that's what it looks like. So R1 is equal to add R2, R3. So add the two registers, what's in the two registers R2 and R3, and put it into R1. And then we have the instruction R4 is equal to subtract R1, R5, which subtracts the value from, accepts the value in R5 from the value in R1, and then stores the result inside of R4. So on the screen here, I show you the two instructions being executed. So here we have two instructions which are being processed concurrently. So we see, according to this diagram, the first instruction goes through the fetch execute cycle, and then the second instruction goes through the fetch execute cycle. So immediately after one time period, the next instruction goes inside of it. So R1, the first instruction starts at 0, and then the second instruction starts at 1. So it's using different parts of the fetch execute cycle. Okay, so what's wrong with this, right? So the two instructions are being processed concurrently. So when you look at this carefully, you notice that there is a data hazard between them. Okay, so specifically from time 3 to time 4. Okay, so the subtract instruction needs the result from the add instruction, which isn't yet available until time 5. Okay, notice because there's an R1 inside the second instruction. So it needs that R1 in order to compute its execute. Okay, so just to say it again, at time 3 to 4, the subtract instruction needs the result from the add instruction, which isn't available until the end, until time 5, where t is equal to 5. So this is called a classic read after write, which is abbreviated as RAW. And the add instruction must first update the value in the register 1, and only afterwards should the subtract instruction read from register 1. All right, so that's what causes this particular hazard. And the way we resolve this hazard is by using something called a stall. And the stall basically delays the subtract instruction until the add instruction completes. Okay, so on the screen now you'll see how the stall instruction can be used to delay instruction 2 in order to allow instruction 1 to complete its execution. So this stall guarantees that the data hazard between the two instructions is resolved, okay, which prevents instruction 2 from reading an incorrect register 1 before it's supposed to read the register 1. Okay, so it only reads R1 once instruction 1 actually updates it. So using a stall does directly cause, it does exactly cause the phases of the fetch execute cycle to remain idle and unused, right? And that's what we were trying to avoid in the beginning. But here, at least there's some level of parallelism, which is more preferred to executing without the pipeline at all. So if we didn't have a pipeline, we would need to completely execute R1 and then only start execute instruction 1 and only start instruction 2 at time 5. Okay, but we can see that we can still we can still do it concurrently. It's just that we would need to include those two little stall periods so that R1 can actually update. All right, so So this is better. This is not ideal because we're forcing different parts to be idle. It's not ideal, but it is better than no pipelining at all. So another really good way of doing this is called operand forwarding. Okay, and also it's also called data forwarding. And here what we try to do is we try to use a technique in pipeline CPUs to reduce the number of stalls that occur due to these type of data hazards. So we have the pipelining ability, but then we try to then use this operand forwarding. So when an instruction requires data that is that is the result of a previous instruction still in the pipeline, we can forward the operand. So it allows the data to be forwarded directly from the pipeline stage to the stage where it is needed. So without waiting for the write back. And that's really the technique that we're going to be using here. So let's look at an example. So suppose that we would like to execute the following instructions. So we've got R1 where we add R2 and R3. We got R4 where we subtract R1 and R5, and then R6 where we add R7 and R8. So if we were to execute these instructions in the order which they appear, then we would achieve a pipeline like this, okay, with stalls. So the execution of the 3 instructions is completed within 9 time units. Notably, even though instruction 3 does not depend on instruction 1 and 2, its execution is delayed since it's the last instruction to be executed. So one way to actually fix that is we can just rearrange the order of the instructions. Since instruction 3 doesn't depend on instruction 1 and 2, we can make it an intermediate one, and that allows us to save some time. So before we would finish at 9, but just moving instruction 3 between instruction 1 and instruction 2, because it has nothing to do with register 1 and it has nothing to do with any of the variables in instruction 2, we can just put instruction 3 between them. And that already saves us time. It allows us to save 2 units of time using parallelism. Okay, so we see that even rearranging them helps. So now let's look at this, the other thing there, which is the forwarding. So before we look at that, let's just talk about the reordering. So the instruction reordering rearranges instructions based on whether they are independent to others. And this here allows us to reduce our stalls. So in this case, swapping instruction 3 and instruction 2 will absorb the execution of instruction 2. And since instruction 3 is not dependent on the outcome of instruction 1, moving it forward in the sequence allows it to be processed without waiting for the completion of the preceding instruction. Okay, so now let's see, how does operand forwarding actually help us here? So operand forwarding can be used to directly pass the result of the operation to the next instruction that requires it. So by passing the so for example, the result of the operation add 2 and 3 in instruction 1 can be immediately forwarded to instruction 2. See, it's the instruction 1, which is the add R2, R3, can immediately be forwarded to instruction 2, which needs the result in the register 1. Can you see the red line? That's forwarding it. We're forwarding the result in the execute directly to instruction 2 on the next phase. And this allows us to bypass the need to write it back to memory. So we can just pass it to the instruction, pass the value to the instruction that needs it. So in this example, the result of the operation add 2, 3, which would have been stored in R1, and R1 was needed in instruction 2, can immediately be forwarded to instruction 2. All right, so this also significantly reduces the delay that would have otherwise be caused by waiting for the completion of the memory write-back phase. Okay, so this is a very simple strategy, and by just doing these simple things, you can really optimize the execution of the instruction by reducing the time constraint. So here's one of the most difficult problems in computer science, and I've introduced you to many of them already. So given a set of instructions, right? So I1, I2, I3, all the way to IN. So these are all instructions like in the previous examples, we looked at 3 instructions. You also can have n instructions, so some finite set of instructions. And each instruction has dependencies in the pipeline processor. So the problem is to find a sequence S, right? The sequence and ordering of these instructions that minimizes the execution time T, which is this, in this case, it's our time. So remember we had 9 units and then we had 7 units and we even saved more time here and there. And so we want to really minimize the execution time, but it has to be, the constraints here is that we want to be able to have all of the dependencies in their orders. So if we need for example here, if we need R1 to be used in instruction 2, then R1 should be updated before instruction 2 executes. And so we need to satisfy these data dependencies. We also want to minimize pipeline stalls. Okay, so these are these white stalls over here. We want to minimize those. We don't want lots of those because lots of those delays the overall process. So we want to minimize that, and we also want to maximize operator forwarding. When an answer needs to be passed across, it doesn't cost us much to do that. We just have to pass it across. So we don't have to write back. We can just pass it across and it'll work. So this is really the problem. We want to be able to find a sequence that satisfies these constraints, but the sequence must be in a minimal time. So it turns out that this is an unsolved problem in computer science. It's a very difficult problem. It's what we call an NP-hard problem. And this NP-hard problem is it's known as it's one of the problems that we'll talk about in the next lecture. Okay. So just to summarize this, the problem is challenging since the number of possible instruction orderings, you can think of the permutations, even ignoring operator forwarding and ignoring incorporating stalls, it increases exponentially. So the number of possible sequences increases exponentially as the number of instructions increase. And that's really why it's a difficult problem. So it's choosing, as your n increases, if n is 100, then how many possible permutations of the input can you possibly have, right? And you can imagine that's a really big number. And 100 instructions isn't a lot. I mean, computers nowadays can execute billions of instructions in their clock cycles. So that's not a lot of instructions. 100 is not a lot. All right, so this problem does not have an efficient solution and is a very important unsolved problem in computer science. If you can solve this problem, you'll also be solving a whole other class of problems which are also NP-hard, difficult problems. You'll know what NP-hard means in the next lecture. So those are all very difficult problems, and solving this problem is very exciting. First of all, you'll get like $2 million from this maths organization overseas. I've forgotten what they're called, but you'll also crack cryptography, and you'll break the internet, and by solving this problem you really will create a lot of other problems, safety concerns, and people won't be able to keep their money in banks and things like that. So it's very exciting, because see, computer science is exciting. Okay, so that's really what I wanted to say about CPUs. And here it's all about this idea of executing instructions. That's really the main theme here. Okay, so now let's talk about the graphics processing units. So a graphics processing unit is really a specialized hardware. Okay, and it's designed for accelerating processing speed in rendering graphical content. So what is graphical content? Remember in the lecture on data representation, we spoke about graphics. And graphics are images. So graphical content has to do with pictures, has to do with visual stimuli. And in modern computers, the GPU's role goes really beyond graphical content. So in the olden days, the graphical processing units was mostly about the like I said, graphical content. But in today's time, we've repurposed the GPU to accelerate processing speed for artificial intelligent learning, right? So the AI algorithms, which also they do something called matrix multiplications, and and vector multiplications. These are all operations which are, you can think of them as grid operations, right? It's numbers in a grid. And what is a graphic? It's also just numbers in a grid. So these GPUs, if they can process numbers in a grid very quickly, then they can also process AI models, which also are represented as numbers in a grid. And they can do multiplication on those grids and division on those grids and other cool operations on those grids that are all really used, which are used to solve really important problems in AI. So now, in this part of this lecture, I'm going to just introduce you to the basic components of the GPU, as well as some heuristics on how it is used. Okay, so the handling of graphics processing is not really limited to the CPU's integrated graphics. So inside of the CPU, there's a little thing there called the integrated graphics, and you can do some graphics processing inside of that. But we have also a dedicated component in a computing system which is often used for graphics processing. So in fact, most computing systems include a dedicated graphics card. So that's a specialized circuit board which is able to handle graphics processing. So on your screen here is an example of a graphics card. And this really offloads the tasks of the CPU, because the CPU is already so busy with its own thing, executing instructions related to programs. Now it should also do graphics. No, it doesn't have to. So there's a specialized hardware, and this graphics card is it. So it allows the CPU to focus on its own, what it's really good at in its own operations. And so this graphics card is now an important component of computing, because it allows us to handle all of the graphics components into one computing component inside of the computer. All right, so the graphics card is really equipped with its own memory. So this memory, just as before we had RAM inside of the CPU, here we have something called VRAM. It stands for video RAM. And another word for it is called the frame buffer. So this memory usually ranges between 8 to 10 gigabytes or more, and it really acts as a buffer between the CPU and the display. So it's like a little place where you can store information, and it's relatively fast. And while information is being processed, it can be stored in VRAM and retrieved from VRAM. Okay, so VRAM occupies about 10 to 15% of the graphics card's physical space, and it's really optimized for high bandwidth to make it faster than the standard DRAM used in the computer's main memory, which we'll talk about later on. Then you get something called GDDR DRAM, which is a type of memory in graphics cards. And this features larger memory buses, more channels, lower power consumption, reduced heat generation compared to the regular DRAM. And that's really necessary, because as you'll see when we talk about the GPU, which is coming up, you'll find that there's like really a large number of cores compared to the CPU. And so having this particular fast memory to facilitate all of the different things that are going on there is very necessary, and it's very useful. Okay, so here's the components of the graphics card, just for you to learn about, and it's just kind of the stuff that's important about the GPU. So let's talk about it a bit more. So the GPU, the graphics processing unit, is actually a component of this. It's a component of this graphics card. So then you see the very first thing there is the GPU, and that really, on the graphics card, it takes out about 5 to 10% of the card space. So it's quite a small space, but that is really where everything happens. So everything else is just fluff compared to what's going on in the GPU. So the GPU is where it's the site for graphics processing. The graphics card also includes capacitors for voltage regulation. It does that through something called the voltage regulator module, VRM. It's on the screen over there, and that takes up about 5 to 10% of the space. And that also connects to the external power supply. The graphics card has cooling, which is managed by a fan, and that's a massive component. It's a large fan that goes on top of it. Here's the So you can just pause and take a screenshot of this or write it down in your book. So I'll go back here, so I'll refer to this picture, it's a lot better. So you see that fan at the top there of the graphics card. It's a big component, and that's important for maintaining operating temperatures. So because you don't want if the GPU gets too hot, remember, it can melt itself because it gets really hot. I mean, I've forgotten the exact number, but it gets very hot. Maybe you can Google it. I think it's even over 100 degrees Celsius. So it gets really hot. I mean, the GPU itself can melt. The metal around the GPU can actually melt. So it needs that fan to regulate the heat, to take out all of that heat so that it can actually operate. Okay, so the connection to the GPU is done using little gold pins that attach to the card, that attach the card to the graphics bus. And I would have shown you an example of this if we had a lecture, but there's if you ever opened up a computer and you took out the CPU, you'll find those little pins, they small little gold pins, and those pins actually attach the GPU or the CPU to the other components. So in this case here, the GPU fits onto the graphics card. Yeah, okay, so there's also external ports on the graphics card, such as HDMI. On the screen you see there's DVI, there's also a display port, and that allows for the connection to monitors. You know what a monitor is, it's the screen. We'll talk about monitors later on too. Each interface has its own bandwidth and frequency capabilities, so that can also influence how much of pixels are being refreshed, or how much pixels can the screen accommodate. So I don't know if you've heard of display ports in DVI, and those, if I'm not mistaken, they can refresh for rates up to 144 hertz. And DVI is only video, while DisplayPort supports multiple video streams, network streams, audio signals, and so on. But the most cost-effective one is HDMI, and it's generally slower than these other types of connections, with a refresh rate, if I'm not mistaken, it's about 60 hertz. Okay. So although the GPU takes up a very small space on the graphics card, it is the most important component. I mean, everything else is supporting this graphics processing unit. Right, that's what I've highlighted here in blue. All right, so now let's move on to the structure of the actual GPU. So the structure of the GPU really accommodates parallel processing of multiple independent tasks. So can you see how big that component is? The blue shaded component. Okay, that is about 40 to 50% of the GPU, and those are what we call CUDA cores. That is really where the parallel processing happens. So I've drawn it as one big box, but there are often hundreds of these cores inside of the GPU. So you can think, just as before when we had the CPU that had these little cores, where did I see the CPU? Yes, it's here. There was core 1, core 2, core 3, core 4, and it was broken up like this. So too in the GPU, you can have all of these different cores. You can have core 1, core 2, core 3, core 4, and each of those cores has this particular profile. Okay, so the GPU really allows for parallel processing and of multiple independent tasks. And it has several key components. So unlike the CPU, the GPU is designed for the rapid execution of a limited set of operations. So your CPU had many different operations. However, in a GPU, the CUDA cores, or the stream processors, they're also called stream processors. These comprise about, I think, maybe half of the GPU, so 40 to 50% of the GPU, and these are really the main processing units responsible for executing parallel operations. Right, so they are very lightweight cores, and they handle a portion of numerical data streams. So if you have like something that needs to be computed, it can be broken up, and each of the cores can tackle a particular segment of it. So let's look at these different, I again have these, what I'm talking about here on the slide, but I'm just gonna refer to them directly here. Okay, so here we have texture units. So that takes about 10 to 15%, that's the blue one, and that handles texture mappings and processing, which is often used for detailed image rendering. Okay, then we have render output units, which are involved in the final rendering stage. These manage the output pixel quality and the image quality. Just as in the CPU, there were cache. So here too, we also have the L1 and L2 cache. But it's a smaller portion. It's about 5 to 10% of the GPU. And this reduces the latency by providing more hierarchical cache memory access. So you have L1, L2, and you can have L3 as well. And those are different types of access. So obviously they have different retrieval speeds and so on. And yeah, so what else is there? So there's memory controllers that manages the data flow between the GPU cores and the external memory, and it interconnects. That's the interconnectors. Did I write it here? Okay, it's fine. It's fine. But those would just connect the memory controllers to the different components so that the GPU can communicate to other components inside of the computing system. Right, then you get the command processor, and this here orchestrates the operations of the GPU. That's the command processor. All right, wonderful. So now let's look at this other one called specialized processors. So these include things like tessellation units and AI accelerators, which allow you to do different tasks in these cores. It assists with providing alternate computational operators, because sometimes you want to be able to do a particular operation, maybe rarely, so you can have a specialized processor that actually does that. And often we're finding more and more GPUs that are being sold today. They have lots of these specialized processors to cater for the large amounts of AI operations which are required for AI computation. So lastly, we have the power management circuitry, and that just really regulates the power distribution within the GPU. So there's a lot of things going on here, right? I mean, the GPU itself is a relatively small portion of the card space, but I mean, it is really the most important component. Okay, so this brings us to another topic, and this topic is the stages of the graphics pipeline. So I'm not going to go into this in detail, okay? Just because for the sake of time, yeah, I really wanted to go through this in detail, but I think for the sake of time, let's not. And what I wanted to show you here is that just as the CPU has the fetch execute cycle, okay, the CPU before, when we spoke about the fetch execute cycle, it was this. Okay, just as the CPU has this fetch execute cycle, so too does the GPU have a particular thing, a particular flow, a cycle, if you want to call it that. And this particular one is called the graphics pipeline. And I've written down here on the side what the different stages of the graphics pipeline is, and I've also had some examples here on how you would do some particular processing within each of these phases. But I think for the sake of I also don't even know if you've covered matrix multiplication and matrix these dot product operations in your maths class yet. So maybe you might not even have done it yet. But I think I'm just going to leave it out. But let's quickly just go through the pipeline to talk about the different things that that are available. So the first thing here, the application level processing, that really handles the initial data. And then the model viewing transforms the 3D models, which are being rendered to the viewer's perspective. Remember that even though you have a 3D environment in your game, on the screen it's a 2D model. Okay, so you're visualizing in 3 dimensions, but when it actually comes to model viewing on the screen, you've got to actually then downgrade it. It's got to be converted. So that part is called projection. Yeah, then also you can there's vertex shading, there's the projection, converting 3D scenes to 2D images, which is displayed. There's then clipping and curling, so parts of the image that you maybe if you think about a video game, maybe behind the table, you're not really going to be seeing that on your screen. So behind the table or behind the cupboard, even though there's something happening there behind the wall, something is happening there. It's not important because you can't see it. So it needs to be clipped out of the viewing experience. So there's this phase called clipping and curling, which is actually how it's done. Then there's rasterization, which converts vector graphics to raster images into pixels, if it's necessary to do so. All of these they're all optional. So some of them are optional, but most of them are actually done, depending on what's being converted inside of the graphics pipeline. But yeah, and then there's ray tracing. But the ray tracing, for example, is one of the optional ones. So this is now really, really cool, and there's a lot of AI that goes into this nowadays. This simulates the interactions of light on realistic image rendering. So, for example, in a game, you might have light coming from a particular angle onto the character or onto the environment, and so ray tracing can really model the physics of that light and see how it bounces around and lights other shaded regions. And so not all games, as you can imagine, have this. I mean, of course, if you have a really good GPU, you can model it, because that's a lot of modeling that goes into the physics of how light behaves. And remember, there's these light, as it moves through the image, it needs to be processed in multiple different directions. So there's lots of processing involved there. So yeah, so the advanced ones can do it. So ray tracing is really exciting. Yeah, and then finally we have then displaying the final processed image. So what I actually prepared for you here is just like for example, here we have transformation. This part here, model viewing and transformation. So then I had, well, you can have a point in a 3D space and it's represented by V, and then you have a transformation matrix which is given to you, and you have to multiply these two things together. And if you do so, then you would have completed the transformation part of the graphics pipeline. And then I had another example here for vertex shading as well. So this is not examinable. All of the stuff is not. This thing's about the graphics pipeline. So just knowing what the graphics pipeline is important, but doing these particular operations is not examinable at this point. Okay, it's just out of your interest, if you're interested in actually looking at that. Okay, so if you wanted to take a break, you can just pause this video and take a 15-minute break. But yeah, I think we're now 60 minutes in. So now I want to talk a bit about computer memory. So computer memory refers to the physical devices used to store data or programs. Okay, so often this is temporary or permanent storage. Okay, so it really depends on what type of memory we're referring to. So memory in computers, they function by storing and retrieving information using a combination of electronic signals, magnetic signals, and optical mechanisms. So all of these different technologies, whether it's electronic or magnetic, this is all really used for memory. And we use these different types of things depending on how quickly they can store information and retrieve information. So that's really what we want to talk about right now. So we're going to start off with something called primary memory. So primary memory is also known as main memory. Okay, so it's often called main memory. So this holds data and applications that are actively in use. It's very different from other types of memory. So the two main types of primary memory is random access memory, right? That's RAM, and also read-only memory, which is ROM. So primary memory is RAM and ROM. So RAM is a type of what we call volatile memory, and it's used for storing data that is being actively processed by the CPU. So an example, so what does volatile mean? So volatile means that it evaporates. So in other words, when the computer is switched off, RAM is wiped clean. So just to say that again, so RAM is memory, temporary memory, which stores data that is being actively used by the CPU. Okay, and so when you switch the computer off, RAM disappears. Everything that is stored in RAM will disappear. So ROM, on the other hand, is non-volatile memory, which means that it's permanent, and it's used really to store firmware and software that rarely ever change. So for example, the program that starts the computer is permanent, so we can store it in ROM, and we can hard code it using special transistors and all of those things, which can make the program non-erasable. So it'll always be on the chip because it's physically there. It's not programmable. It's physically there. Okay, so data in ROM is read-only. It remains intact even when the computer is turned off, and it's usually used for really important, so small programs, but important ones, which are maybe operating or the boot, when the computer turns on, there's some kind of program needs to run. Okay. So typically ROM has, like I said, it's much smaller capacity than RAM. So when we talk about RAM, there's two types of RAM. There's dynamic RAM, which we refer to as DRAM, and then there's static RAM, which is SRAM. Okay, so this one on the screen here is known as DRAM, so dynamic random access memory. So this is the type of RAM. And this is primarily used in main system memory in computers. So it provides space for the operating system to do its thing, some applications, some active processes. Mainly the operating system constantly uses it because while the computer is in action, the operating system is really the thing that's holding everything together. All right, so a DRAM chip consists of millions to billions of cells, each containing a transistor and a capacitor. Okay, so here's the transistor at the top here and the capacitor at the bottom. So the transistor in these cells are extremely small and maybe only a few nanometers across. So unlike the typical NPN transistors which you've seen before with the base, the collector, and the emitter, the transistors in DRAM cells are what we call field effect transistors, so FETs. And these primarily consist of a gate, a source, and a drain. So that's the one that you see on the screen. So each memory cell in DRAM is made up by connecting the drain of the transistor to the capacitor, which stores the electrical charge. So the capacitor can quickly charge and release energy. So the other end of the capacitor is connected to the ground, so as it shows in the screen. So this configuration, right, allows the cell to store a little bit of data. Okay, it allows to store a bit of data in the form of a charge. So the charge state of the capacitor represents one binary state, which is a 1. So in other words, if the capacitor is charged, then it stores a 1. Okay, now remember the capacity is being drained. Every nanosecond that passes by, it's draining. So obviously it needs to be refreshed, okay? But we'll get to that. So the capacitor is storing a 1 if it's charged, and if it's discharged, it stores the other binary state, which is 0. And this way, the transistor acts as a switch that controls the charge and discharging of the capacitor, and thus the cell is being stored. Okay, so this is really what's on the screen. Right, okay. So something I mentioned already is that the capacitor, when it's discharged, it's a 0, and if it's a 1 if it is charged. But then also remember that it is a capacitor, so it is losing information. It is losing, electrical voltage. So it needs to be refreshed. And let me see if I put a picture here. Okay, so here is an example of DRAM. And DRAM, so now all of these transistors, you put them together and it gives you this DRAM, which is this dynamic RAM that we're talking about. So here each bit of data is stored in a separate capacitor within an integrated circuit. So for example, look at the word line at the top. You've got all of these transistors. You've got 1, 2, 3, 4, 5, 6, 7, 8. So that's one bit. Okay, so you have the 0th position of the bit, which is the first transistor. On the right hand side, you've got the next bit. On the next one, you've got another bit. So altogether, you put those bits together, you got 8 of them, it gives you 1 byte. So this is 1 byte of memory. So you can store a number in there. You can store 1011 1100. Okay, so that's four bits. So the architecture of DRAM is really organized as a matrix of rows and columns, just like it is here. And this matrix is navigated using 2 components. We've got these word lines on the right-hand side, on the left-hand side, sorry. The left-hand side, the word lines. So it says word line 0, word line 1. And we got bit lines. So the bit lines is bit line 0, bit line 1, bit line 2. So remember, a word, in this case here, is a single byte. So word lines are used to select a specific row of memory. So that means that the bit lines, on the other hand, are used to read data from or write data to selected cells. So we can use these word lines and these bit lines to basically access each individual cell inside of DRAM and update it. So if we want to update a particular cell, we simply emit a charge into a word line and then into a bit line simultaneously, and then we can charge a capacitor or release the charge from the capacitor, basically changing a 0 to a 1 or 1 to a 0. Okay, so I hope you're finding this interesting. I mean, this is basically how DRAM works. Yeah, so to write data, the DRAM controller activates the appropriate word line. This allows the row of cells associated with it. Then it drives the bit line to the desired high or low voltage levels, right, representing a 1 or a 0. The capacitor in the selected row are then charged or discharged to store the corresponding bit value that we want to store. So that's how we would write data. And to read data, it's very similar to, we got to activate a word line, right? So that connects the row of the capacitor to the respective bit line. And then as the capacitors share their charge with the bit lines, a small voltage changes on the bit line, and that's what is used to detect the amplitude of the signal in the capacitor. So these voltage changes are then interpreted as binary data, either a 1 or a 0. So I'm telling you this, I'm not going to test you on this. I'm telling you this so that you know how DRAM actually works. So what am I testing you on? So I'm not going to ask you to state the process of how data is written in DRAM and discharged, interpreted as a 0 or 1. I'm just letting you know that this is actually a very principled process that we are talking about here, and it's not magic, right? It really works, and it's really an interesting, intriguing process. Okay, so that's how DRAM works. It uses these transistors. So what I want you to remember here from our discussion on DRAM is that DRAM uses these specific type of transistors, and it organizes these transistors into a grid. And there's a mechanism that writes information to those transistors by charging the capacitor. And when the capacitor is charged, it's going to be a 1, and when it's not charged, it's going to be a 0. And those are the main takeaways there. Those are your examinable takeaways. Okay, the actual technicalities is fine. I mean, you can, if you're interested in learning about them, then go ahead and research them. Yeah, it's really interesting stuff. So now let's talk about the other type of RAM. So we said it's DRAM. So now another one is called SRAM. So that's called static random access memory, so SRAM. And that uses a memory circuit known as a flip-flop for each memory cell. So we spoke about flip-flops in a previous video. But in this video here, I've stuck one here on the screen. So unlike DRAM, which stores a bit of data as a charge in a capacitor, okay, from the previous slide, SRAM stores a bit of data in a latch. So this is an example of a latch, the one that's on your screen. So to demonstrate how a latch stores a bit of data, you can look at the video I did on gates and circuits, and there was something like the sequential circuit here, where we had these NOR gates. And these NOR gates, we use these NOR gates to basically store a latch, to store some information inside of X. And depending on how we set our S and our R, we would change the value of X, and making sure that we never use the forbidden state. Okay, so the only thing I want to really discuss in this one, so for this, a more detailed discussion, please go to that video and you'll learn exactly how this works. It's a nice video. It took me a lot of time to make that video. I hope you actually watch it and enjoy it. Okay, what I want to talk about is this. I don't think I mentioned this inside of that video. So having these two inputs, S for set and R for reset, this can lead to an unintended state change in the basic SR latch. And this can happen because of noise and glitches. So for example, what I'm saying is that if I have S to be 1 and it has a glitch and it switches to 0, then that's actually a big deal. That's actually a big problem, because that means it's going to be changing X and not X at the end. And that's all because of noise, electronic noise and glitches that occur. Okay, so we can solve this problem by using something called gated SR latch. So the gate here is the AND gates that are basically added to the beginning. And this incorporates an additional control input, so the control input, right? And this is often referred to as an enable or a clock. And these single input controls the value for R and S simultaneously to prevent these race conditions from occurring. So, and so the idea behind having this particular gate, these AND gates here, is to basically say that if my S is a 1, right, and my E is a 1, then only then will the output be a 1. Okay, and so if S changes because of some kind of glitch, then it'll still be it'll be interpreted as a 0. Okay, so let's look at an actual example of this. Did I have an example here? Okay. So I didn't have an example here, but let's just try to go through this as a simple example, right? So just to give you a basic idea of what's going on here. So only when E is in the write enabled state, okay? So you can be in a write enabled state or not. And E is really what is causing this to be gated. So when E is in a write enabled state, which means that it's set to 1, then only then can R and S's lines store a bit in X. Okay, if E does not allow R and S to store something, then it'll be set to 0. If we want to be able to use this gated latch, we must first allow E, or we first have to make E 1 so that S and R can operate. So for example, if E is 1, right, then S can be input as 1 and the output can be a 1. Okay. When E is then switched off, then S and R can no longer influence the network. There's no value of S and R which can make the output of those AND gates a 1 if E is going to be a 0. Okay, that's the big takeaway. Okay, so yeah, so that's basically it for gated latches. It's just to protect the integrity of the circuit. And so what else do we need to talk about? Yeah, so there's different types of read-only memory. So I spoke a lot about RAM. I didn't speak a lot about ROM. So there's different types of them. There's this PROM, EPROM, EEPROM, and these are all different types of them. And I just put it up here so you can see that they are different types, even though I'm not going to talk about them in a lot of detail. But yeah, I mean, some ROM you can reprogram, you can erase it using UV light, and some ROM you can erase it electrically. So obviously, it comes with different advantages and disadvantages. So, for example, the EEPROM, which can be electrically erased and programmed. Let's say that the booting software of the operating system needs to be changed. Then the manufacturer will take the computer and they can electrically erase it, and then they can put they can reprogram the booting operation, right? So you could have that. That's a EEPROM, but obviously that's more expensive, right? And you don't want to increase the computing components, the prices of the computing components. I mean, computers don't even last that long. Every 5 years, you've got to get a new computing component or a new computer entirely, because maybe the other components are no longer talking to each other properly. So you would need to then actually update the different components of the computing system, or update it completely. So having parts which are expensive is not always a good idea, especially when you're replacing it all the time. So sometimes EEPROM is used, and I've written some use cases there. So for example, it's used for data storage where frequent updating is required. Okay, so that's when we would want to actually use EEPROM. Maybe I don't know if you remember Windows Vista, but it was like a disaster, and we kept it kept having lots of crashes. And then Windows 10 came out, Windows 8 came out, Windows 7 and Windows 8 was really good, and then I think they skipped Windows 9. But anyways, my point is that depending on how much of a disaster the operating system is, we might need to always update our BIOS or any other types of programs which require RAM. Right, so that's really the story about ROM, sorry, not RAM. Okay, so I'm actually going to now move on to a different type of memory. So now we're looking at something called secondary storage. And secondary storage serves as storage for data that is not actively in use. So it stores data which maybe it's a program which you've never used. It's there, you know it's there, but you don't use it. It's just sitting there on your hard drive. So so it's not actively in use, and there's really two ways we can store data like that. We can store it in hard disk drives, which is this one here. And today also we've got something called solid state drives, which is SSDs. So we'll talk about these two, and these are important ones in modern computing. So let's start with hard disk drives. Okay. So your hard disk drive is a storage device, and this consists of several components. So these are all of the components that you can see on your screen. So the body of the hard disk drive provides the structure that houses and protects all of the internal components. So that's the gray area. Inside of this structure, we've got the platter, where data is stored magnetically. So can you see where it says platter? That circular thing, that's where the data is actually stored. And here we use electromagnetic signals. So before, remember, for the transistors, we used capacitors. Now here we're using magnets. So this particular disk is a flat circular disk, and it's made of a non-magnetic material. So usually aluminium or glass, and it's coated with a thin layer of magnetic material. So that magnetic material is where we're going to store things. So the data is stored on these tracks. So where it says tracks, which are these circular on the surface of the platter, and each track is divided into smaller units called sectors, representing the smallest storage unit on the platter. So it's stored on those sectors. And then you've got a spindle, and that spindle is the axis around which the platters rotate at a constant speed. So it must rotate at a constant speed so that we can calculate how much to turn the platter in order to find information in the different sectors. So reading and writing information is performed by something called the read-write head, which is that little pin part of the actuator arm. It's mounted on the actuator arm, and it's positioned very close to the platter surface. So the actuator has something called an actuator axis. Okay, I drew these diagrams myself. It took a long time to draw them. So the actuator axis actually controls the movement of the read-write head across the platter. Okay, so that's how it moves around. And the seek time is the time it takes for the read-write head to move over the correct track to read the data from. Okay, so I'll say it again. The seek time is the time it takes the read-write head to move over the correct track to read data from. All right, so it must move over to the correct track. So once the head is over the correct track, the data must then be accessed from the right sector. And the time it takes for the desired sector to rotate in a position under the read-write head is called the rotational delay. So there's some terminology that you actually need to know about. So this terminology is also in the textbook, so I'm not too worried about it. So the total time required to read or write data, right? This is known as the access time, and this includes the seek time and the rotational delay. So you add those two together, you get the access time. So this metric determines the overall performance of the hard disk drive. So additionally, the transfer rate is the rate at which the data is transferred to and from the platters, and this rate will depend on the rotational speed of the platters and the density of the data storage. I have an example here of I think I've got an example here. Yeah, okay, I've got an example. Can I just see if I can write on the screen? I hope I can. Let me see. How do you do that? Okay, so I go here, draw. Is it working? Oh, wonderful. Okay, so let's look at this particular question. So it says here, consider a hard disk drive, okay, with an average seek time of 9 milliseconds, a rotational speed of 7,200 rotations per minute, okay, and a transfer rate of 100 megabytes per second. Okay, so we need to calculate the rotational delay. Okay, and that's the time for one complete revolution. All right. So we're given that the rotational speed here is 7,200 rotations per minute. And the time to complete one rotation, one revolution, which is what we're trying to do, which we're trying to compute, is, so let's call it the time to complete one revolution. Okay, so that's easy, right? It's going to be 60 seconds divided by 7,200 rotations per minute. Let me just let me get my calculator. Okay, so then that's going to be about 0.00833 seconds. Okay, so it's 8.3, which is about 8.33 milliseconds. Okay, so then the average rotational delay will be half the time of the complete revolution, as the sector can be anywhere on the disk. Okay, so we can just say then that this is approximately, so the average rotational delay divided by 2, must I write it down? Yeah, I think so. So the average rotational delay is equals to 4.17 milliseconds. Okay, and so then the excess time should be the sum of the average seek time and the average rotational delay. So the average seek time is 9 milliseconds from before. So let me write this down. So the average seek time, where is this thing? Average seek time, yeah, okay. Average seek time the excess time, not the average seek time. My bad. Uh-oh. Okay, so I'm gonna have to write it down again. So this is approximately 4.17 milliseconds. Okay, so the excess time is the sum of the average seek time. I'm writing in a very awkward position, so sorry about that. Average seek time plus the average rotational delay. For some reason I can't write on that side. Okay, so that's going to be about 9 milliseconds plus 4.17 milliseconds, which is about 13.17 milliseconds. Okay, so yeah, so that's basically it, right? I should have added some more to this question, but the rotational delay. Okay, so the transfer rate of the HDD is about 100 megabytes per second. Did I say that? Yeah, okay. So that indicates how quickly data can be read to and from the drive after the read-write head is positioned over the correct track. And the access time determines how quickly the hard drive can begin the data transfer process. And the transfer rate then dictates the speed at which the data is transferred. Okay, so that's basically how you would calculate something like this. And there's lots of other examples like this. Like I could ask you also how much of capacity, and this is an important one, how much of capacity does the hard disk drive actually, cater for? So the capacity is the number of bits, or you can even measure it in bytes. So if I say there's 4 platters, and if I give you how much of data can be stored per sector, and if I give you how many tracks there are, then you must remember also that on a platter, here's the platter in the previous question. This platter here, sometimes you can have 4 of them stacked on top of each other. And the read-write head goes between these different platters. It's like a rack of read-write heads that go between these platters, and they read information from there. But the thing about a platter is that you can write information at the top, and you can also write information at the bottom, because it's just magnetic. So you can have these 2 sheets for one platter where the read-write head can interact on the top and the bottom. So when you're calculating the capacity, you must be able to multiply the platters times 2, because each platter can have data at the top and at the bottom of the platter. So that's the platters multiplied by 2, multiplied by, then you have your, by the blocks and the sectors and the tracks. And then you'll know how much of data can actually be stored in a hard drive. Okay, so calculating capacity is something I didn't ask you to do, but you should know how to do that. Okay, so we're actually covering quite a lot of concepts, and I don't blame you if you want to take a break and come back. But we're almost done. I think there's about maybe, how many more? There might be about maybe 5 slides left, so we're almost done. We really just need to talk about these solid state drives, do a little summary about all the different types of memory that I've talked about, and then we can talk about the input and output. So the motherboard, summarize all of this memory stuff, and then the input and output. I mean, input and output is a breeze, right? You all know about that already. Okay, right, so where was I? Okay, so I was talking about these solid state drives. So an alternate for hard drives is the solid state drive. And in a solid state drive, we've got something called a logic board. That's the green thing that you see here. It's where all of the different components of the solid state drive actually sit. And yeah, so the important thing here, the things that I've actually highlighted here, is that we've got these things at the bottom of the solid state drive called the SATA connectors. And that is the interface that connects this SSD to the motherboard. So the motherboard, really, people call it the backbone, because that's the place where all of the components sit. It all comes together through the motherboard. The motherboard brings all of the different components together. And the SATA connectors is what connects this SSD to the motherboard. Then next to the SATA connectors, you've got a power connector. That's what powers the actual SSD. And we've got flash memory, and this is NAND memory chips, which is a bit different from the, it's not NAND as in the NAND gate, it's NAND as in a different type of NAND. But these memory chips, it's flash memory. Then you have a logic board, where everything actually fits into. You also have a controller chip, which is in charge, making sure that everything talks to each other, and well, as the name implies, it controls the activity of the SSD. And then finally, we have this little cache chip, which allows us to store some information in. So cache, whenever you hear the word cache, it's just another place where you can store information. Okay, so these you can actually have these NAND memory chips on both sides of the SSD. Okay, so if you flip this logic board over, you're going to find more of these different ones. So what I've done for you here is I put together all of the different components that we've spoken about, and some that we haven't spoken about that you've already might be familiar with, on a table, so that you can physically look at this and measure the performance gains, the size, the storage capacity, even stability. You'll be surprised how long certain things actually last. For example, here at the bottom, you got all of your movies on your hard drive. Did you know that a hard drive, the life expectancy is between 5 and 10 years? Did you know that a CD is between 25 and 50 years? And after that, it might stop working, right? It degrades. Yeah, so, okay, so on the first column, I've got the storage type. I've got SRAM, DRAM, flash memory, no memory, and there's also the different types of flash memory. There's NAND, there's the NAND, which is typically what these chips use. and then there's also NOR, okay, which is a different type. Then you got CDs and DVDs, Blu-rays, HDDs. The ones I omitted, which I should have actually put it here, are magnetic tapes, which they used to use in the olden days. I don't know if you remember the time where people stored information on these cassettes, which was like a magnetic tape. And the really old cars used to have these tapes that go into the car and plays music, and then sometimes when you go over a bump, then you hear a scratch, and then if you're really unlucky, then all of the tape starts coming out of that. All of the magnetic tape comes out of that cassette, and it's a big nightmare. But surprisingly, those tapes actually last a lot longer than CDs and DVDs. In fact, I also see vinyl. These vinyl discs are becoming more and more popular, and those also, they last quite long. And you'll be surprised to hear that that's actually a continuous way of storing information, not a digital one. Right. So this tells you about the life cycles. It tells you about stability. It tells you about storage space and so on. Okay, so this is an interesting thing to know. I feel like, if you're doing computer science, if somebody asks you what's the difference between a CD and a DVD, and if you don't know, then that's a bit of a problem. Okay, so just to give you one of an example from here. So in flash memory, for example, the NAND flash offers a life cycle of about 10,000 to 100,000 read-write cycles. Okay, so you can put stuff on it and take stuff off it. So read-write, we call it a read-write cycle. Okay, and up to 4 terabytes of storage per chip, and it has a high speed of 3,500 megabytes per second. So which of these is the fastest? So where's the fastest one? Is it DRAM? No, it's SRAM. Okay, so the SRAM, that's the one that's inside of the, those are inside of the cache. We typically use that for cache. Okay, and it's just a few megabytes of data, but it's extremely fast. Okay, I mean, if you want to talk the fastest, it'll be obviously registers, right? Just having a byte of information stored in a register in the CPU. Okay, but here now we're talking about SRAM, which is typically used for cache. DRAM is typically outside of the CPU. You have NAND storage and NOR storage, which is used in SSDs, and CDs and DVDs and hard drives, which are more of the ones with moving parts. Right there, you've got to have a read-write head, and it also decreases the speed. Okay, so have a look there that the CD, the DVD, Blu-rays, HDDs, they're at the bottom of the table, and there's a reason for that, because they have moving parts, and when you have moving parts, you have physical constraints. Whereas in SSDs and flash memory and these MOSFETs and so on, they don't really require it. Okay, so that's it from that side. Okay, so what else do we need to talk about? We need to talk about motherboards. So a motherboard is least talked about, but also a very important component of computers. So when you're picking a computer, how many of you actually look at the motherboard? How many of you actually look at the motherboard and say, maybe I need this motherboard instead of that motherboard? Okay, I'm willing to bet that most of you look at the RAM, and most of you look at the CPUs, and also most of you look at the GPUs. But it turns out that a motherboard is pretty important too. So that really serves as the platform for all the hardware components. So it not only does it do that, it also coordinates operations between the components. So it coordinates the operations among the CPU and the RAM. Remember, we were talking about that in the CPU, there was that data bus and there was the memory bus. And those things, that's the RAM, right? There's special cables that are inside, that's all of the motherboard. There's special cables in the motherboard which enabled the CPU to talk to RAM. Okay, so the motherboard is extremely important. That's my point. Okay, so it houses the CPU socket, for example, right? That's basically where the pins go in. It goes into the component in the motherboard. So it has the RAM slot inside of it. So the motherboard has space for the RAM. So do you see this on the screen? We've got the RAM slots. We've got the CPU socket. Okay, we've got expansion slots for components like graphics cards. Your graphics cards fits onto the motherboard. It has connectors for USB devices, for audio peripherals, for networking hardware. What else does it do? It includes the power delivery system, which you can see on the screen, that little green area there, that distributes power to the different components as well as to itself. It has a BIOS and a UEFI chip for system initialization. When the system starts, that's the BIOS chip. It sits on the motherboard. So that's you can think of that as being a little bit of ROM, where a program is hard-coded into so that it can start the actual computational process. Yeah, and it traces the wiring of the printed circuit board, right? So that motherboard connects all of these different components. So the traces and the PCB, that's really now that is not just a little like before, this connects all of these components in a very intelligible way. Okay, right. So that's really the motherboard. It's a very important component. Okay, so in the olden days, we used to have on the motherboard, we had these north bridges and south bridges. I'm sure you've heard of those before. And those were really, they used to refer to specific chipsets responsible for managing various system functions. Okay. However, in modern computers, these chipsets have largely been replaced. Okay, and this is because we've gotten really good at representing transistors using semiconductors. And so having that separation in the motherboard just became more of a hassle. So we actually just removed it. Yeah, so I mean, you're not going to be examined on these specific things that I'm talking about, but knowing about the basic components and how they interact with each other is important. Okay, all right, so that's it for motherboards. So I've written down the components here and what do they do. So this is examinable, and yeah. The last thing I want to talk about is devices. So I've got two different types of devices. There's input devices and you've got output devices. So the input devices, what I try to do here is put them into different classes. So I've got pointing devices. You can think of that as your mouse. You can also think of those as your pen, your Apple Pencil, whatever. It's a pointing device, right? So you can actually touch the screen and it points to a particular region and you can write on that particular region. And so that's a pointing device. So we also have keyboards. You're familiar with keyboards. You've seen them before. I'm sure you have. A keyboard is how you can input textual data inside of the computing system. It has all of the different values, some of them from ASCII. You have you have a T, you have the hat symbol, you've got the, looking at my keyboard, I'm trying to think of the name of that one. I think it's called an ampersand. And there's also backslashes and commas and lots of other things. So the traditional one that we use, most people use, is the QWERTY keyboard outline, but there are others as well. And you'll find even in our department in computer science, some of the lecturers prefer to use their own special keyboards. And those keyboards, remember, the QWERTY keyboard is popular because it was one of the ones that it's just like, when something is the first one, it becomes popular because people are gone used to using it. But there's actually a lot of other keyboard designs which are scientifically shown to be more efficient and allow you to type faster even than the QWERTY keyboard, which is the one that we all use. I mean, the MSL building is full of these QWERTY keyboards, and I have one in my house too. But yeah, that's just one of many other different keyboards, which are also input devices. Okay, so there's number 3 here. There's joysticks and gamepads. I don't think I need to tell you about what a joystick is or a gamepad. I think you know what it means. All of you, or maybe 90% of you, have played a game before in your life on your phone or on a PlayStation. To be honest, I haven't really played a game on a PlayStation, or maybe once or twice, but that's about it. So you are much more experienced in using joysticks and gamepads. Yeah, what else do we have? So we can also perceive input. So I'm sure you noticed that your phone can also record information, and that can be put as input. So for example, sound that you hear, or your camera can take detailed videos. They can serve as input as well inside of the computer, which can be processed. You have scanners, like for example, when you when you, I don't know, why would you need to use a scanner as a student? I don't know, maybe you collect all of your different notes and you scan them in to make them digital so that they're easier, or they can go on your iPad. So that's a reason to do it. Yeah, so you can scan documents, and that's an example of an input. Sometimes you can scan documents and enhance them. You can digitize documents. Maybe at home you've got a lot of photos. Now that's a good example. It's something I had to do a couple of years ago. You've got a lot of photos, and now you have to scan everything in because you know that one day it's going to get missing and you're going to miss all of your pictures. So you scan all of them in. It takes you like 3 days or 3 weeks, depending on how many pictures you got. And then yeah, so now, and then you can even enhance them. You can, maybe the color wasn't so good because it's an old photograph, so you can do some basic image processing to make the color a bit more snappy. And yeah, we also have these biometric inputs. So when you come onto campus, you input your fingerprint, or you wave your hand over the fingerprint scanner, and it takes a picture of your fingerprints and analyzes it to see if you match, if you're on the database, so that they can open the gate for you. So that's another example of an input device. So you can see I've kind of classified them into, and if you feel like I've forgotten one, please let me know and I can include it. Because, you know, I would, like I told you, I'm writing a book and I need to make sure that all of these things are actually, I have a good representation of the different things. So yeah, okay, that's always a good idea. All right, the last thing here is the output devices, and I think here also you're familiar with all of these. So we have these visual display units, like the ones that I'm looking at right now. It's a monitor, and you have LCD ones, you've got LED ones, OLED ones, and so on. They're all different types of ways that monitors are constructed. We have output devices as well, like speakers and headphones, and on our phones we've got speakers. If you listen to music and you don't want anyone else to listen to your music, then you can put a headphone on. It's also an example of an output. There's much more sophisticated ones too, which are both input and output. If you've heard of noise cancelling headphones, it has input as well. It takes in the sound, reverses it using something called a Fourier transform, and then after that it plays it back so that the sound coming into your headphone is cancelled by sound coming out of your headphones. So that's an input and an output device, and that's those noise cancelling headphones. So we also have these physical output devices, like proper scanners, like the normal scanner. You've also got 3D scanners now, 3D printers. And there's physical output devices also in factories where they manufacture a lot of different types of products, and that can be seen as an output device as well. So for example, the machine that manufactures glasses, for example, right? It has a specific way of taking material, converting input material into output material. That is also an output device. So we have, so think outside of the box in terms of what the capabilities of processing, because computation is any kind of process. So if there's an input and an output in that process, then those are input and output devices. Okay, so the last thing here is VR headsets, which is which has become popular. I don't know if it's still popular. I remember people were talking about VR headsets, virtual reality headsets, and everybody was doing bungee jumping in their living room. But then what happened after that? I think the next big thing was augmented reality, where you had games like Pokemon Go, and you could use your camera to find little Pokemon because they augmented the camera input with a object, so that you had like something on your object, and that's always augmented reality. And yeah, so those are all examples. I mean, even an output can be part of the input. For example, in augmented reality, the input is coming in as what we call your perceived input, but then it's being augmented with objects. The perceived input is being augmented by objects to produce an output. So there's these new types of. So I think I need to update this, but there's lots of different output devices out there. Okay, so that's it from my side, and I think in a normal lecture it would be 45 minutes and 45 minutes. So maybe we're even a bit shorter than what we were supposed to be in. But there was a lot of information here. So that now, you might be worried, now what am I going to study, right? So, okay, so first of all, the textbook has a whole chapter on this stuff. And it talks about the different components, and they might even go into more details. And so I really want you to get the high level descriptions of how these things actually work. However, where I want you to really go low level, go much more detailed, is here. When you talk about the fetch execute cycle, this is something, and also all of this stuff, right? So when it comes to the CPU in general, right, all of this, right, the CPU processes, how instructions are taken and moved around, it goes into these different states, how do these pipelines work with stalls, how is operator forwarding, how it works, what is the pipelining problem, why is it a difficult problem, right? Those are the most important, okay? Everything's important, but those are the most important. And then everything else you can think of as secondary importance, which is also examinable, except for all of this, and I told you that when I was discussing it, all of this stuff about the graphics pipeline. But yeah, so just make sure that you know all of the relevant parts. So like, for example, this was important. I spent a lot of time talking about it, and this too. And I kind of like also gave you tips on how much to focus on this, because obviously this you can go as deep as, I mean, you can go and start talking about MOSFET architectures in DRAM and how the capacitors, how the electrons are moving from, and how it's grounded, how the electrons, you could go into that level of detail. Speaking about electrons, I mean, even if you talk about quantum computing, there's specific types of devices there that can hold data in the form of 0 and 1. So there's lots and lots of scope to go crazy deep into these ideas. But I'm telling you what to focus on. So for example, this year, I wouldn't really ask you to repeat these definitions or these properties, right? I mean, but I would expect you to know your way around the CPU and how these processes are interacting and how these instructions are executed and what are these different components. What is the memory address register? What is the program counter? What is the address bus and the data bus? What is memory in this context? What is the purpose of the instruction decoder? What does the arithmetic logic unit need in order to be able to do the execution? And all of these different things. Okay, so I think that's it from my side, and good luck with your studying on computing components. I will publish one more lecture on the limits of computation. And then after that, you'll have everything you need to study for your exam.